An improved S-box generation method using Metaheuristic optimization technique. Shubhankar Vashishta. Computer Science and Engineering SRM Institute of Science and Technology Chennai, India. Abstract substitution boxes, S-boxes, are a crucial nonlinear component in modern block and stream ciphers' cryptanalytic resistance. Due to their relevance, there is a wide range of S-box construction techniques. The success of EASE, Advanced Encryption Standard, posed cryptographers with new challenges in creating powerful substitution boxes using various underlying approaches. There are various parameters that play a vital role in creating a robust S-box that is secure enough to use, which includes nonlinearity, differential uniformity, absolute indicator value of global avalanche characteristics, bits independence criterion, BIC, confusion characteristics, transparency order, etc. We can obtain the desired value for a parameter by using various optimization techniques like Pso, GSA, etc. In the proposed scheme, Metaheuristic optimization technique will be used for setting the values of the above-mentioned parameters. Keywords: S-box, particle swarm optimization, Gauss Iterated Map, cryptography. Introduction. The protection of private data and visual information have been a major concern for years, given the transparent and vulnerable nature of web and networking technologies. Since many years, the cryptographers have proposed different types of information protection methods. Depending on how information is interpreted, encryption techniques can be divided into stream and block ciphers. 1. A block cipher is a method of text cryptography where the encryption key and algorithm are applied to the block of data at one time, called blocks, with an invariable transformation. The block cipher uses permutation and replacement layers to design efficiency that shows high uncertainty and scattering properties. For such networks, substitution boxes are crucial components intended to convey the necessary nonlinear data transformation, that in turn contributes to better uncertainty and strength to various cryptographic attacks. The substitution process utilizes block bits for input and nonlinearly converts them into various block bits for output too. It is indeed a linear conversion of the input sequence, as opposed to shuffling, which refers to the permutation process. The advancement and improvement of proposals dedicated to the development of substitution boxes has contributed significantly to the success of the EASE block cipher as well as its substitution box 3. They are stable, with structures that emphasize on algebraic strategies, optimization, chaos function as well as structures, and so on. A dynamic and open problem is the design of effective and variable size S-boxes. The scale of the massively bulky search space is one of the essential causes of this difficulty. As a result, a chaotic metaheuristic optimization approach is constructed to develop a competent framework of an S-box with varying size that can produce effective S-boxes. The initial conditions and control parameters of chaotic systems are highly sensitive to these systems, which is why they are regarded as good origin of entropy. They have strong responsiveness to preliminary constraints and system specifications, as well as quick autocorrelation and arbitrary nature of produced data. 2-4. Even small adjustments in the preliminary constraints and governing conditions have a significant impact on performance, making chaos-based structures ideal for the development of robust encryption algorithms. Chaos-based mechanisms, on the other hand, can never exhibit chaotic behavior to every value of the preliminary constraints and governing conditions. 5. The chaos-based behavior of the selected scheme is the first requirement inside the architecture of chaotic encryption algorithms. Therefore, when choosing initial conditions and control parameters, caution must be taken. The chaos-based structure's preliminary constraints and governing conditions are real valued in the interval in which they are described. And it has a vacuum of infinite value. Optimization algorithms are needed to pick the optimal chaos-based framework through this unlimited search space. 2 preliminaries. S-box parameters. 1. Nonlinearity. The least separation of a Boolean function f to the collection of each affine function is used to calculate its nonlinearity measure. 6. As a result, standing nonlinearity scores should be reflected in the S-box constituent functions. The nonlinearity NLFN for each Boolean function fn is evaluated with EQ 1. 13 equals 12, 2-1, where max fn is known as Walsh-Hadamard transform of Boolean function fn. 7. If a Boolean function has weak nonlinearity, it is called fragile. The increase of nonlinearity of stable Boolean functions is regarded as among the most important steps offering control resisting linear attacks. 7. Table I lists out the nonlinearity of the sum the S-boxes used in this paper to compare the nonlinearity of the proposed scheme. Table I comparative analysis of nonlinearity of 8x8 S-boxes. 2. Differential uniformity. The differential uniformity compares an S-box's resistivity to differential cryptanalysis. Beham and Shamir defined the cryptanalysis attack technique, which involves creating a disparity in the I/O distribution for pupils of attacking block ciphers in S-boxes 8. If the XOR value of every output has similar uniformity to the XOR value of every input, then the cryptanalysis can be completed. 9. When the input/output distribution of an S-box is uniform, it is said to be immune. In the XOR table, the greatest value of differential uniformity, do, shall be kept low. Do of any Boolean function fn, x, can determined by 13. Equals maximum, 0, number, equals 2. Where set y contains every possible input value and its components have a figure of 2n. For an S-box, the largest value of the XOR table should be small enough to prevent cryptanalysis. Table 2 compares the differential uniformity of various chaotic substitution boxes. B. Gauss Iterated Map. Gauss Iterated Map is one of the most popular one-dimensional chaotic map. It is a simple function which displays chaotic behavior with discrete time domain and real space domain 10. It is dictated by the EQ, 3. Where a and ss are the control parameters which govern the bifurcation and xn is the function variable. The Gauss Iterated Map produces best results when the value of a is set between 4.5 to 8 and the value of ss lies between -1 to 111. Figure 1 shows great chaotic characteristics of Gauss Iterated Map for a equals 6.2. Screenshot_11.png. Figure 1. Bifurcation of Gaussian map at a equals 6.2. Figure 2. Flowchart of particle swarm optimization. See particle swarm optimization. Particle swarm optimization, PSO, is a metaheuristic optimization algorithm that was proposed by Eberhard and Kennedy in the year 1995. The model was influenced by studying the behavior of fishes and birds. PSO has been used in a wide range of optimization problems, both alone and in conjunction with different algorithms. 12. Each particle obeys a specific path, being a positional vector that depends on time. Two major key pieces consist of the swarming particle's movement, a stochastic bit and a deterministic bit. By differentiating the paths of these discrete particles, PSO explores the domain of an objective function. Every particle is drawn closer to the current global best position, G, and its personal best known position, while at the same time showing a tendency to shift impulsively over time. The particle modifies the position as the best new particle present I when it finds a position that is better than any location previously found. At any given moment, at each iteration, there seems to be current best for every particle. The main goal is to discover the best global solution from all of the existing best solutions until they stop improving or after a certain amount of iterations. Let the position vector and velocity be represented as 11 and 6 respectively for the ith particle. The EQ, 4, defines the new velocity vector. +1 equals, +1 1, +2 2, asterisk dash. 4. Where and denotes the position and velocity of ith particle at t times. R1 and R2 are two arbitrary vectors with values ranging from 0 to 1. The parameters c1 and c2 are the constants of acceleration, usually equal to, say, c1 c2 2 for balanced approach in its stochastic and deterministic way. The initial positions of all the particles should be distributed sufficiently uniformly so that they can be sampled across most regions. We can then update the new location using the EQ, 5. Here, 6 can take any value. However, it is generally bounded within a certain range 0, V max. 3. Proposed work. The Gauss Iterated Map is used to spawn the first population of the S-boxes. The two parameters and are set to 6.2 and -0.38 respectively in EQ, 3. The reason for utilization of these particular values lies in the chaotic nature of the map. The Gauss Iterated Map shows exemplary bifurcation for above specified values. The Gauss Iterated Map is also used to achieve the control parameters, K1 and K2, of the PSO. The research indicates that incorporating chaos through adjustment vector update contributes in a better search area exploration and use and can improve standard of the output influence the chaos-based initialization and updating of PSO parameters. 13. Steps for the PSO technique are as follows. A. Creating the vector of population. Every distinct S-box is considered a single entity. Using chaotic maps, the initial population of S-boxes is created. The size of the original generated population is kept small according to the heuristics mentioned. 14. The initial population, i.e. n, is hence set to 40. B. Setting the fitness parameter. The fitness value for the problem is determined by a specific parameter. The nonlinearity of the S-box, particle, is observed as fitness value in the population vector in EQ 4 and EQ 5. See Initializing the Vectors. The adjustment vector is defined at the start and modified after each iteration. Each place vector initializes the values of the respective S-box in the sample. As per the EQ 4, the adjustment vector is modified. For each S-box, the best personal vectors are determined. The recently created S-box in the sample which has a higher fitness value than the preceding S-box is updated as the personal best vector. The S-box with the highest nonlinearity in the population is used to describe the global best vector, GB. The E's S-box is set as global best, GB, in EQ 4. The nonlinearity for E's S-box comes out to be 112. The reason for selecting E's S-box for global best position is due to the fact that it is one of the most widely used S-box having extraordinary resistance to various cryptanalytic attacks. D setting parameter values. PSO parameters like R1 and R2 are kept constant at 0.9 in EQ 4. The control constants, K1 and K2, are randomly initialized with the chaotic value provided by the one-dimensional Gauss Iterated Map for the EQ 4. The selection of control parameters is left upon the chaotic map for increased unpredictability and dynamic range of output. During the optimization process, these parameters are modified after each iteration. The PSO inertial parameter Z is initialized to a 0.7 in EQ 4 for the best optimization results. This parameter helps in concentration of the S-boxes in accordance to the respective nonlinearities. E pre-processing and adjustment. The equations 4 and 5 are used to update the adjustment vector in S-boxes for each iteration. This procedure generates certain repeating and negative values. The solution values for the S-box architecture, on the other hand, are limited to a range 0,255. As a result, we use a pre-processing and adjustment method to eliminate the possibility of repeating and negative values. Negative values are manifested in the desired range during pre-processing using some mathematics. To preserve the bijectivity of the S-boxes, we look for repeating values during the adjustment process and replace them with missing values 15. The nonlinearity values are updated for the newly created sample. Optimum nonlinearities are maintained and sent to the recently updated sample, which is double the size, i.e. 80, of that of the original sample, from the current sample. NGB are revamped, as previously stated. Adjustment vector is denoted by for the ith S-box and TTH iteration. Initial values 4, plus 1 equals, dash, 2, plus. Gaussian map initial value, xn equals 0.231. Gaussian map parameters, a equals 6.2, ss equals minus 0.38. In order to simulate, evaluate, and optimize the output of the proposed method of generating an S-box, we use the input arguments of the method proposed. The suggested approach is evaluated by changing sample range, iterations, and inertial parameter under various scenarios and conditions. The number of iterations for optimization is set as 100. For performance analysis, a total of 4,000 S-boxes were generated and optimized by particle swarm optimization technique. The S-box in Table 4 is the best outcome among the generated S-boxes. For the values of various initial parameters, the minimum value of nonlinearity of S-box comes out to be 104. The same S-box displays the differential uniformity of 8. However, another optimized S-box, shown in Table V, with nonlinearity 102, displayed better differential uniformity with value 6. Various S-boxes from the literature are compared on the basis of nonlinearity and differential uniformity shown in the Table 3. Figure 3 shows the competence of the S-box security scheme proposed in this paper. The fact that an S-box is bijective means that it is a one-to-one mapping. That is to say, all feasible resultant vectors shall emerge only once. Since each 256 possible resultant value is unique and show up one time, both S-boxes in Table 4 and V preserve bijectivity. For S-boxes that are used in block ciphers, one of the key problems in the world of cryptography over the last 2 decades has been the construction of extremely nonlinear S-boxes. By using the suggested PSO-dependent approach, we can achieve S-boxes that are very similar to the 8x8 S-box with nonlinearity as high as 112/16. Differential cryptanalysis can be restricted for an S-box demonstrating minimal do 8. Our S-boxes are measured with differential uniformities of 8 and 6 for S1 and S2, respectively. Table 3 shows that the proposed S-boxes have greater capacity than other S-boxes to reduce differential cryptanalysis. The proposed S-boxes therefore have due efficiency and demonstrate considerable resistance to differential cryptanalysis. Figure 3. Comparison of nonlinearity. Figure 4. Comparison of differential uniformity. Table 4. Proposed S-box S1. 99. 124. 119. 123. 242. 107. 111. 197. 48. 1. 103. 43. 254. 215. 171. 118. 202. 130. 201. 125. 250. 89. 71. 240. 173. 212. 162. 175. 156. 164. 114. 192. 183. 253. 147. 38. 54. 63. 247. 204. 52. 165. 229. 241. 113. 216. 49. 21. 4. 199. 35. 195. 24. 150. 5. 154. 7. 18. 128. 226. 235. 39. 178. 117. 9. 131. 44. 26. 27. 110. 90. 160. 82. 59. 15. 179. 41. 227. 47. 132. 83. 209. 0. 237. 32. 17. 30. 91. 106. 203. 190. 57. 74. 76. 88. 207. 208. 239. 170. 251. 67. 77. 51. 133. 69. 40. 2. 127. 80. 60. 159. 168. 81. 163. 64. 143. 53. 157. 56. 245. 188. 182. 218. 33. 16. 66. 84. 210. 205. 12. 19. 236. 95. 151. 68. 23. 146. 167. 126. 61. 100. 93. 25. 115. 96. 129. 79. 220. 34. 42. 144. 136. 70. 177. 184. 20. 222. 94. 11. 196. 224. 50. 58. 10. 73. 6. 36, 92, 194, 211, 172, 98, 145, 149, 214, 121, 231, 200, 55, 109, 141, 213, 78, 169, 108, 86, 219, 234, 101, 122, 174, 8, 186, 120, 37, 46, 28, 166, 180, 198, 232, 221, 116, 31, 75, 189, 139, 138, 112, 62, 181, 102, 72, 3, 246, 14, 97, 228, 87, 185, 134, 193, 29, 158, 225, 248, 152, 238, 105, 217, 142, 148, 155, 243, 135, 233, 206, 85, 244, 223, 140, 161, 137, 13, 191, 230, 65, 104, 249, 153, 45, 252, 176, 255, 187, 22. Table V proposed S-box S2. 124, 119, 123, 242, 111, 197, 48, 1, 103, 43, 254, 215, 171, 118, 202, 130, 201, 125, 250, 89, 71, 240, 173, 212, 162, 175, 156, 164, 114, 192, 183, 253, 147, 38, 54, 63, 247, 204, 52, 165, 229, 241, 113, 216, 49, 21, 4, 199, 35, 195, 24, 150, 5, 154, 7, 18, 128, 226, 235, 39, 178, 13, 9, 131, 45, 26, 27, 110, 90, 160, 82, 59, 214, 179, 41, 227, 47. 132. 83. 209. 0. 237. 32. 252. 177. 91. 106. 203. 190. 57. 74. 76. 88. 207. 208. 239. 170. 15. 67. 77. 51. 133. 69. 249. 2. 127. 80. 60. 159. 168. 17. 22. 64. 143. 146. 157. 56. 245. 188. 182. 218. 33. 16. 30. 40. 210. 205. 12. 19. 236. 95. 151. 68. 23. 196. 81. 117. 61. 100. 93. 25. 115. 96. 129. 79. 220. 34. 42. 144. 136. 70. 126. 184. 20. 222. 94. 11. 219. 224. 50. 58. 10. 73. 6. 36. 92. 194. 211. 172. 98. 145. 149. 163. 121. 231. 167. 55. 109. 141. 213. 78. 169. 108. 86. 244. 198. 101. 122. 174. 8. 186. 120. 37. 46. 28. 166. 180. 200. 232. 221. 116. 31. 75. 189. 139. 138. 112. 62. 181. 102. 72. 3. 246. 14. 97. 53. 87. 185. 134. 193. 29. 158. 225. 228. 152. 234. 105. 217. 142. 148. 155. 238. 135. 233. 206. 85. 243. 223. 140. 161. 137. 248. 191. 230. 66. 104. 65. 153. 44. 251. 176. 84. 187. 255. V. Conclusion. This paper implies that an effective optimization-based S-box approach is an alternative to spontaneous and algebraic approaches. The S-boxes for high nonlinearity as fitness value are developed with particle swarm optimization. This approach uses the chaotic Gauss Iterated Map for original sample generation and other necessary arbitrary values. The procedure was investigated by changing the parameters of the Pso for various scenarios. The proposed method was shown to be capable of producing solid, well-encrypted S-boxes. Compared with many recent S-boxes, the proposed S-boxes have been found to be upstanding enough than many of their contemporaries. Thus it is possible to create strong nonlinear S-boxes using the proposed technique. 6 references. 1. Yiping Zhang, Jizhu Sun, and Su Zhang, A Stream Cipher Algorithm Based on Conventional Encryption Techniques, Canadian Conference on Electrical and Computer Engineering 2004, IEEE Cat. No 04CH37513, Niagara Falls, ON, Canada, 2004, pages 649 to 652 Volume 2, doi, 10.1109/Xees.2004.13451996. 22 M. Ahmed, E. Al-Solami, A. M. Al-Ghamdi and M. A. Yusuf, Bijective S-boxes method using improved chaotic map-based heuristic search and algebraic group structures, in IEEE Access, Vol. 8, pages 110,397 to 110,411, 2020, doi, 10.1109/Access.2020.3001868. 3. Mohammed, Kamsia and Pazi, MNM Pazi and Ali, Fakaria. And Arifin, Suryani. 2014, Study of S-box Properties in Block Cipher, I4CT 2014-1 Tons International Conference on Computer, Communications, and Control Technology, Proceedings. 10.1109/I4CT.2014.69142006. 44Z. Hua, B. Zhou and Y. Zhou, Sign Chaotification Model for Enhancing Chaos and its Hardware Implementation, in IEEE Transactions on Industrial Electronics, Vol. 66, Number 2, pages 1273 to 1284, February 2019, doi, 10.1109/Ti.2018.28333049. 55 J. Sprott, Elegant Chaos Algebraically Simple Chaotic Flows. Singapore, World Scientific, 2010. 66 M. Ahmed, N. Mittal, P. Garg, and M. Moftab Khan, Efficient Cryptographic Substitution Box Design Using Traveling Salesman Problem and Chaos, Perspect. Sci. Vol. 8, pages 465-468, September 2016. 77 W. Cusick and P. Stanica, Cryptographic Boolean Functions and Applications. Amsterdam, the Netherlands, Elsevier, 2009. 88 E. Beham and A. Shamir, Differential Cryptanalysis of Day. Like Cryptosystems, J. Cryptol, Vol. 4, Number 1, pages 372, January 1991. 99 M. Ahmed, C. Volas, M. Daha, and M. Beg, a new hyperchaotic system-based design for efficient bijective substitution boxes, Entropy, Vol. 20, Number 7, p. 525, July 2018. 1010 K.Sakthadesan Sankaran, G.Amu and V. Nagarajan, Non-Local Image Restoration Using Iterative Method, IEEE International Conference on Communication and Signal Processing, ICCSP14, April 2014, pages 1740 to 1744. 1111 A. Sahai and C. Pradhan, Gauss Iterated Map-Based RGB Image Encryption Approach, 2017 International Conference on Communication and Signal Processing, IXP, China, India, 2017, pages 0015 to 0018, doi, 10.1109/Xp.2017.82864337. 1212 Yedong Zhang, Shuhua Wang, Zhenlin Ji, A Comprehensive Survey on Particle Swarm Optimization Algorithm and its Applications, Mathematical Problems in Engineering, Vol. 2015, Article ID 931256, 38 pages, 2015. doi.org web link. 1313 M. Ahmed, I. A. Kaja, A. Baz, H. Al-Hakami and W. Al-Hakami, Particle Swarm Optimization-Based Highly Nonlinear Substitution Boxes Generation for Security Applications, in IEEE Access, Vol. 8, pages 116,132 to 116,147, 2020, doi, 10.1109/access.2020.3004449. 1414 QBI, Analysis of Particle Swarm Optimization Algorithm, Compute. INF Sci. Vol. 3, Number 1, p. 180, January 2010. 1515 Wang, Yang and Lei, Peng and Wang, Kuo, 2015, A Method for Constructing Bijective S-Box with High Nonlinearity Based on Chaos and Optimization, International Journal of Bifurcation and Chaos, 25, 1550127 doi, 10.1142/S0218127415501278. 1616 J. Damon and V. Richman, The Design of Ryundale, is the Advanced Encryption Standard. Berlin, Germany, Springer Verlag, 2002. 1717 D. Lambic and M. Nikolic, Pseudo-Random Number Generator Based on Discrete Space Chaotic Map, Nonlinear Dyne, Vol. 90, Number 1, pages 223-232, 2017. doi, 10.1071/S11071-0173656-1. 1818 M. Khan, T. Shah, H. Mahmood, and M. Gondal, An Efficient Method for the Construction of Block Cipher with Multi-Chaotic Systems, Nonlinear Dyne, Vol. 71, Number 3, pages 489-492, 2013. 1919 G. Joachimowski and L. Kokorev, Chaos and Cryptography, Block Encryption Ciphers Based on Chaotic Maps, IEEE Transaction Circuits SYSTI Fundam. Theory APPL, Vol. 48, Number 2, pages 163-169, February 2011. 2020 G. Chen, Y. Chen, and X. Liao, An Extended Method for Obtaining S-Boxes Based on Three-Dimensional Chaotic Baker Maps, Chaos Solitons Fractals, Vol. 31, Number 3, pages 571-579, 2007. 2121 I. Hussain, T. Shah, and M. Gondal, A Novel Approach for Designing Substitution Boxes Based on Nonlinear Chaotic Algorithm, Nonlinear Dyne, Vol. 70, Number 3, pages 1791-1794, 2012. 2222 G. Chen, A Novel Heuristic Method for Obtaining S-Boxes, Chaos, Solitons Fractals, Vol. 36, Number 4, pages 1028-1036, 2008. 2323 D. Lambic, A Novel Method of S-Box Design Based on Discrete Chaotic Map, Nonlinear Dyne, Vol. 87, Number 4, pages 2407-2413, 2017.